We're talking discrete and continuous. We just visit these again. Discrete, as you put in your notes, they're countable things. How many books you have on your desk? How many people walk past this room? Those are the countable objects. Continuous, things that happen in between. Think of it this way. If you can say to yourself, do I have a 1/2? Then you have continuous. Okay? If not, do I have to count whole numbers? You have discrete. What we do in this course is mostly discrete probability. It rains 1 day, it rains 2 days, it rains 3 days. We look at the whole numbers. We don't say does it rain 1 1/4 days. So we're going to be doing discrete probability distributions. Just so that you recap that, this is kind of the easy part. Decide whether this is discrete or continuous. Let X represent the number of Fortune 500 companies that lost money in the previous years. Would X be a discrete variable or a continuous variable? Discrete, what am I counting? The number of companies. So I have to count those in whole numbers, right? I have to say 1 company, 2 companies, 3 companies. Okay, so count them in whole numbers. Let X represent the volume of gasoline. Continuous. Can I have a 1.5 gallons? Can I have a 1.3 gallons? 1.2 gallons? Yep. Or volume, can I have 23 point something volume? Yep. X represents the speed of a rocket. Is it continuous or discrete? Continuous. X represents the number of cats born on a farm in 1 year. Discrete. I can't say I have 1.5 cats born. Right? Okay. So those are the things that we had to look at. This part is important. Hopefully you emphasize this in your notes. To make a discrete probability distribution, you have to have 2 things present. The 2 things present must be that your probabilities fall between 0 and 1, but we already know that. We know all probabilities fall between 0 and 1, and that the sum of all your probabilities add up to 1. So if you're looking for rolling a dice and you want the probability of getting a 1, getting a 2, getting a 3, they all have to be written as probabilities between 0 and 1, and the sum of all the possibilities has to equal 1. These 2 things must be present for us to do this. We must have satisfied these conditions first, and then we can kind of move on. Once you make your distribution, and it just looks like a frequency table, same kind of setup, we use in fact, it's very, very close to your relative frequency, because how do we get probability? How do you get a probability out of something? Put it over the total, part over whole. Same as your relative frequency. So we're going to make a frequency distribution. We're going to count off the little tally marks. We're going to sum up your frequencies. We're going to basically do what your relative frequency says, part over whole. And we're going to check that each of them are between 0 and 1, and that the sum is 1. If you've counted for every part that could happen, every case, you have to add up to 1 at the end. Alright, so let's take a look at this. This is in your book, too. And they give the graph, and they give the picture on page 192. On page 192. An industrial psychologist administered a personality test for passive-aggressive traits to 150 employees. We need to keep track of how many employees we use. This is your N. The individuals were rated on a score from 1 to 5, where 1 is extremely passive and 5 is extremely aggressive. And a score of 3 was your neutral score, neither trait. The results are shown in a table. The table's at the left of their example. They want you to construct a probability distribution for your random variable. Now, this is exactly the same as we did your relative frequency. So where they're going to put this column, you could very easily put this column right here. P of X. These have to add up to what? Well, the total frequency. How many workers or people did we survey? 150. So probability is the same as relative frequency, part over whole. 24 over 150. 33 over 150. It's nothing that you haven't done. We're just now calling this a probability distribution versus a relative frequency distribution. It's going to graph the same way. It's going to look the same way. Okay? They entered it on a separate line, but you can enter it either place. And they round to 3 decimals. This one rounded to 2 decimals and didn't go anywhere else. So this one was fine. But if you have to, round to 3 decimals. If it has to go any further. And then 2 more. 0. These have to be between 0 and 1. These are your 2 stipulations. Between 0 and 1, they are. We made them that way. They're part over whole. And their sum has to be 1. Okay? It's no different than your relative frequency graph. No different. In fact, if you remember back, when we put these in your L1, and we did this, L1, L2, we could have also done this, L1, L2. It's going to come out the same, except for one thing. Does anybody remember the one thing that doesn't come out if we use your probability as your L2? Think back to your standard deviations. When you do a sample for your standard deviation, you divide by n minus 1. N, if we did this, what does our n add up to? 1. Our n over here adds up to 150. So when we do 1 minus 1, we can't do 1 minus 1. So therefore, it's not going to have a sample standard deviation. That's the only difference in this whole thing. No sample standard deviation, if you do that one. They go through in this unit the whole way of using the chart when we first found standard deviation. We'll just walk through it, but because you have calculators, there's really no need for you to do them out manually. I just want you to see where they come from, though. So these are the things that we're looking at. And then when we graph these guys, we'll take a look at what their graphs look like. If you look at page 192, you can kind of see their graph from their passive aggressive. It models close to a normal curve. And we'll look for any skews. We'll look for, where the tail goes, if it models a normal curve. And there's something we're going to test in a little bit. So these aren't anything new for you, just things that we have done. So let's have you guys try it too. You're going to, I calculated all those for you. I put them out there. And hang on, I have a chart for you. I have a chart for you to put these on. Because we're going to work more with it. Kind of nice because it adds up to 100. So it makes life easier for your decimals. So Jared, you want to give me the first 3?
I think I did it wrong.
Okay, what'd you get?
I got 0.
Okay, so what are you supposed to do? Add these all up.
Yeah, I didn't add them up.
Nope. Add these all up and put 16 over 100. They all kind of work out nicely because they're 2 decimals. They're over 100. So 19 over 100. How do I write 9? 0, 9. 10, 8, and 2. What should these add up to? 1. Okay, these are all between 0 and 1. The 2 things that I need to make this a probability distribution. They have to be between 0 and 1, your probabilities. Probabilities can never be negative, can never be greater than 1. And they have to add up to 1. This kind of worked out nicely because they were based on 100. Now, to make our probability distribution graph, we do it the same way as we did your relative frequency graph, basically. Same way. We're doing a bar graph, only we write our sales down here. These are our sales per day. We change this up just a little bit. And your probability goes over here. We give this a title, number of sales per day. But your X values have to go here. Generally, we use 0, so meaning the none. Sometimes we don't get a 0, such as the traits. They didn't give us a 0 there. But if we're calculating how many days this happens, we usually get the 0. Your y-axis has to go as high as 21. So space it out a little bit and go by 0.05 if you can fit it in. Whatever your graph can fit in. It's just like your relative frequency, except we change your x-axis around a little bit. We have no upper class or anything like that. We put your x values on there. And make your bar graphs. Make your bars with the 0 and the numbers here in the middle. So this goes up to 0.16. 1. It's the same concept, we just change it up just a little bit. Okay. So we take a look at your probability distribution graph. And what would you say? Is this represent a normal curve? Does it have a skew in it? What do you think? Skew to the, follow the tail. Skew to the right. This is a little skewed to the right. It means most of your numbers came up here, not down in the lower numbers. It was kind of on the beginning part had the higher numbers. So this is skewed to the right, kind of follows the tail. It's just like your relative frequency, except again your x-axis just a slight bit different. Okay. And same thing, we always give it a title, we always label the axes, and so forth. Not a lot different in this. Okay, verify that these are probabilities. What are the two things we're looking for? Add up to 1. And the individuals go from 0 to 1. So the first thing we can eyeball is, does this go from 0 to 1? All your probabilities? Yeah? Is the sum 1? So add them all up and see if they sum up to 1. Yes. So therefore, this is a probability distribution. This works. Kind of a silly way to look at it, but we're just figuring out if it's a probability distribution. Okay. Verify the one that we constructed. If we constructed it and we did part over whole and we knew the total, should ours work? If we did it the right way, part over whole? Yep. Okay. Take a look at this guy. See if this one is a probability distribution. Number 1. No, because why? It adds up to 1.07? Okay. So, nope, this is not a probability distribution. How about number 2? Nope, which one stands out? -1 stands out. What other one? 5/4. This guy's a negative, can't have a negative, and you can't have a value greater than 1. It's got to be between 0 and 1. So two things have to be present. And we don't have to continue doing those. Now, this is a little bit different to find the mean. They find their mean a little bit different. And we can absolutely find our mean the same way that they do. Or we can just look in your calculator and find your mean that way. So take a look at how your book suggests to find your mean. We're on page 194. To find your mean, they say take the total, of the x's times the probability. Technically, it's not really the same. The chart that we just did, or this is the chart that we did. Let me see if it's there. Where's my chart? Where's the chart? Okay. Their chart, if they wanted to find a mean for this, all they're saying is to do this. Take this value. Oh, take the x value times the p of x, and then add them all up. Take the sum of those. So they're saying to do this. This column is going to say x times p of x. So 1 times 0.16, 2 times 0.22, 3 times 0.28, 4 times 0.20, 5 times 0.14. They're going to take that up. They're going to add the whole thing up. They kind of wrote it all out here. So 0.84. You see what they did? We're going to do it on the calculator. But just so that you know, you can get it off this chart. They add it all up, and they come out to 2.94. And this is their mean. It's a nice way to do it without putting it in your L1. Take your x times your p of x. Take the sum of that. They should have put it this way. Not the sum of the x's. The sum of the x times the p of x. This column, it comes out to be the mean. You can absolutely put this in your calculator. L1, L2. L1, L2, or L1, L2. The only difference is with the decimals, you're not going to get a sample standard deviation. The only difference. Okay? So just so that you know, we can make this column and we can find the mean that way. And sometimes we might as well do it. We can do it. Okay. So again, this is how they calculated it. 1 times 6.16, and then they sum this up. Really, they should put this here. Oh, I don't know why it's not letting me write on this. They should say it that way. The sum of the x's times the p of x. That gives you the mean. It gives you the mean in your calculator as well, so we'll probably just use the calculator. Okay. So your chart that you did. Let's have you do the next column. We did the one column. Let's have you do the next column. Continue with the one we just had. Do the x of the p of x. This was yours. Humor me and do this times this and put it over here. And then let's add them all up. And then let's put them in your calculator and see if they come out to be the same mean. This guy times this guy, put it here. This was our x variable. How many sales per day? Just bear with me for a second, just so that you know where it comes from. There's your x, there's your p of x. We calculated part over whole. We got your p of x. We calculated your mean. Your mean came out to be 2.6. 1 minus 2.6. There's your mean up here. well, this is their example, so I don't know what their example was. 1 minus this, then they took the squares, then they multiplied the p of x times the sum of the squares, and they came out, sum of that row came out to be your variance. It's kind of similar to where we take the standard deviation of the other ones, the difference of the mean and the x, we square it, we add them all up, we divide it, and we go through all of that. I just want you to be aware that they're able to do this. I don't ask you to know it, just so that you know that somewhere we're able to get through this part. But I don't really have you do this. We can absolutely do this on your calculator. If we can do it on your calculator, no sense for us to do it. Seriously. Okay. And again, I'm not going to ask you to do the chart. Unless you want to. Anybody want to? No. No. I can't slide this down. Okay, this part is important. This part's the important part. Expected mean. Kind of breeze through this unit pretty fast. Not a lot to it. It's the next part that we get really moving on. Here's your expected value. And you probably remember writing this out in your notes. The expected value of a discrete random variable is equal to the mean of the random variable. Very, very basic sentence. For some odd reason, I'm just having issues with my board today. So the expected value is basically your mean. If you make your chart, it's your x's, your sum of your x's, times your p of x. Okay? And very, very basic. It wants to tell you, if you keep doing something, what did you expect to gain overall? Or lose overall? Like if raffle tickets, lottery tickets. Those are where they do expected values. You pay so much for a ticket. Most of the time you lose, but sometimes you win. Does that win offset all the things I would lose? That's what they're looking at. You know, some people spend hundreds of dollars in lottery tickets every week, and they get all excited. They win. They get some winnings. But overall, what is their net gain or loss? Is what we're looking at. What is your expected value of all of this? So we figured out very, very, very simply for us. So this is how we figure this out. We say, so for instance, this raffle ticket. We sell 1,500 tickets. They're $2 each. There's 4 prizes that you can win. You can win a $500 prize, a $250, a $150, and a $75. You buy 1 ticket. What is the expected value of your gain? Okay. Over time. So now, if you won the $500, you still spent $200. So your expected gain is, oh, I swear. And it won't let me move this down. Okay. So your expected gain is $4.98 because you spent the $2. Okay? And again, if you won the $250, you spent the $2. If you won the $150, you spent your $2. You won a $75, you spent your $2. And if you had no winnings, you still spent $2. So because there's only one ticket you purchase, you have a 1 out of 1,500 chance of winning that particular prize because you only bought 1 ticket, not 4. You bought 1. So 1 out of 1,500, 1 out of 1,500. All the rest of these guys are losers. So you didn't win. So that's how small your chances of winning are when you calculate these out. Now, one step further, they say, fill this box in and just multiply these out. This times this. This times this. Just like we did your x times your p of x. And then what did we do? We totaled it. Because it's your mean. So we have the same process here. Yes. Well, because out of 1,500 tickets, 4 of them are winners. Then 1,500 minus 4 are losers. Out of the 1,500 sold, only 4 are winners. So these guys are losers. You only have 4 winners. So if we do this, do you see how this matches up to your mean? It's the same exact thing. We do all this, we multiply them down, and we add them all up. And they did this in your book, so I don't need to multiply it all out. This last guy has most of the losing tickets here. So you came out with an expected value. Once you multiplied them all out, and then you added them all up, or you put them in your L1 and you put them in your L2, and you calculated your mean, you had an expected value of negative $1.35. And how they interpret this is, because the expected value is negative, you can expect to lose an average of $1.35 for every ticket that you purchase. Overall, if you purchased all these tickets, do it in your head this way. If you purchased 1,500 tickets, how much did this cost you? $3,000, right? Could you possibly win back $3,000? So overall, you'll lose. Your expected value, you can't win. Overall, you're going to lose on this particular case. In some cases, you may break out winning. Some cases, you may break out losing. But you know that little wise guy that says, I'm going to buy all the tickets so that I can win all the prizes. But you're still going to lose money. So your expected value, should that happen, was $1.35 per ticket that you're losing. So it's kind of like the same situation that we do your mean with. The x times the p of x, and then we take the sum of that. It's the same as if we put this in your calculator as your L1 and your L2. Okay. Same difference. We can put it in your calculator, L1, L2, and get your expected mean. Let's have you try one and see what it looks like for you. Try 7 at the bottom of 196.